Good morning. Welcome to the Austin chapter of Reasons to Believe. My name is John Murphy. I currently serve as the president of the Austin chapter, and I'd like to open our monthly meeting with a word of prayer real quick. Dear Heavenly Father, thank you so much for this time that we can gather together and we can virtually connect as a chapter during this very trying time. Ask that you please be with everyone who is suffering through this Arctic blast at the moment. And that we're so thankful that we have shelter and we have heat and that we're able to survive this. Please be with Dr. Ross as he presents this morning, that you give him the wisdom to convey the information that you want us all to hear. And please be with us in our hearts and our minds, that we are receptive to his word and how we can take that and we can improve this planet that you've so graciously given us. In Jesus' name we pray. Amen. Let me go through a few announcements real quick before we introduce Dr. Ross. So if you're not already familiar with Reasons to Believe, I want to first give a shout out to Worldview Media, who is hosting this event for us. We're so very thankful to have Jorge in South Carolina. We have Diego in Costa Rica. We have Dr. Ross in California. And we have myself here in Georgetown, Texas. And so thankful to Worldview Media being able to put this together. And I would encourage you that if you want to use them to host a chapter meeting, or if you have a virtual conference, to reach out to Jorge and Diego and ask them what they can do for you. They've been fantastic for us. Again, if you're not already familiar with Reasons to Believe is a science faith think tank that is based in California. If you go to the website, which is reasons.org, you'll see that RTB's mission is to spread the Christian gospel by demonstrating that sound reason and scientific research, including the very latest discoveries, consistently support rather than erode confidence in the truth of the Bible and faith in the personal transcendent God revealed in both Scripture and nature. And while you're at the website, I would encourage you to visit our chapter page. So if you click on the Get Involved button, that'll take you to this page where you will simply click on the RTB chapters. That'll take you to this page where you scroll down and you find the Austin, Texas chapter. When you click on that, that'll take you to our chapter page. And so here you can see our meeting location where we normally have in-person meetings on the second Saturday of every month. You will also see our schedule and the calendar of events. So we usually advertise our future presentation coming at least 3 to 4 months in advance. And we really are so looking forward to going back and returning to our in-person live scholarly presentations like we've been able to enjoy. For example, when Dr. Erica Carlson came from Purdue University and talked to us about quantum mechanics. Dr. A.J. Roberts came a year ago this month. She's an epidemiologist, and that made for a very fascinating conversation as this pandemic started to unfold. And she has gone back to work at the National Institute of Health to help us during this pandemic. We also had Dr. Michael Strauss from the University of Oklahoma. He's a particle physicist. And so, again, I would encourage you to stay on top of our calendar and our schedule, and hopefully sometime later this year, we'll be able to return to those in-person meetings. Now, while you're at the RTB website, I encourage you to go to the store where they have pages and pages of books and videos that are available, and especially want to highlight Dr. Ross's book, Weathering Climate Change, which will be the topic of his conversation today. So if you enjoy this presentation. It'll just be a microcosm of what's actually found in his book. I would encourage you to go to the website and order the book. And then finally, I'd also like to invite you to partner with the ministry. If you press the donate button, you can see multiple ways that you can partner with us to spread the Christian gospel through science and scripture. You can make a one-time donation, or perhaps you can even join as a monthly partner. I'm currently a monthly partner, which means that I give a fixed amount to the ministry. And so I have the joy of participating in the ministry. But there's also sometimes the occasional perk as well. So sometimes when they have a new book or a new DVD that comes out, I'll often receive one in the mail just as a thank you gift for being a monthly partner. So again, I would like to ask you to prayerfully consider joining the ministry and partnering with us. So last month was the first part of a two-part series on prayer and miracles. And so we looked at the question, does prayer work? That presentation is now on our YouTube channel, and so I would encourage you that if you missed that, to go back and check that out, as well as other presentations, past presentations that we still have on our channel. For example, in September, the former atheist Dr. Sarah Salviander presented on how we should look at Genesis 1. And then back in July, we were very fortunate to have the former atheist and cold case detective J. Warner Wallace speak to us. His topic was God's crime scene. I think that may have been the best virtual presentation I have ever seen. I was thoroughly impressed, and I would strongly encourage you to go back and check that out while you're on our channel. Next month, we'll continue with part 2 of our series on prayer and miracles, and we'll look at the question, is it rational to believe in miracles? We're going to be looking at several specific events in which I believe that the laws of nature may be powerless to explain, and so please join us for that. If you missed part 1, go back and watch that first. I would encourage you. And then in April, very excited to have Dr. John Franklin Lane come and speak to us. This is a little bit different than what we normally do here at our chapter meetings. Often we talk about philosophy and science through biology or physics or one other category. We're going to hear an incredible testimony, and I'm going to talk about it more at next month's meeting as we try to promote that in advance. But I will tell you this, that this is a story you will never forget. Lacey and I, my wife, were able to hear a condensed version of his testimony, only about 20 minutes. He's going to be able to speak for 45 minutes, and there's a whole lot more about his life and his testimony that I'm very much looking forward to hearing. So I would strongly encourage you to circle your calendar for that event. And then in May, we are just thrilled to have Dr. Walter Bradley back. Dr. Walter Bradley is one of the most respected Christian apologists that is living today. We are so thankful that he has retired here in the Austin area. He's become a member of our chapter, and he has so graciously agreed to speak to our chapter about once a year. And so in May, he'll be looking at what happens when we die, and he'll be offering a scientific perspective. And imagine that's going to be very informative. So again, I would encourage you to circle your calendar. So after Dr. Ross's presentation today, I would encourage you, we are going to have live Q&A, so I'd encourage you to make a note of our email address, which is reasonstbaustin. TB stands for to believe. So again, it's reasonstbaustin@yahoo.com. We'll try to get to as many questions as time allows after Dr. Ross presents. So if at any point during the presentation you have a question, go ahead and send it in, and that way we'll have it ready and available to go when he is finished. So at this time, I would like to invite Dr. Ross. I'm so thankful to have Dr. Ross here to speak at our chapter. I'm going to try and switch back here. There we go. Dr. Ross, thank you so much. You know, a year ago when we scheduled this, we were expecting you to be live and in person, and we were very much looking forward to that. It's always a treat to have you here. But like so many things last year, we've had to adapt and change, and so very thankful that you were willing to join us here virtually today. I don't know if you remember, but the very first time that we met personally was after you and Dr. Rana debated Michael Shermer at the University of Texas My wife Lacey and I were newbies to Reasons to Believe at that time in the local chapter, and could not believe that we had the opportunity to volunteer to take you and Kathy to the airport after that debate. I felt like a U2 fan being able to take Bono to the airport after a concert. I just could not believe that we had that one-on-one opportunity. And it was such a thrill to be able to hear the backstory of the debate and to hear some of your thoughts on how it went and how it was different from previous debates with him. My only regret was that I didn't think about taking the long way to the airport. So we could have enjoyed your time much more. And I will say this, every time that we've had a chance to visit with you personally, whether it be at a dinner or that ride or any of our chapter meetings, I've always been so impressed by your humility and your wisdom. And so we really are so grateful that you're willing to share your wisdom with us again today. Thank you.
Hey, you're very welcome. Looking forward to this.
That's good. Well, I'll turn it over to you at this point.
Okay. Yeah, just a brief introduction. My background is in astrophysics. I also serve as a pastor on the pastoral staff of a church that's in between the California Institute of Technology and the Jet Propulsion Laboratory. In fact, every Sunday I run a class for skeptics and atheists called Paradoxes. It's been going now for 4 decades. And, what I like about being between Caltech and JPL is we always have engineers and scientists, and also we're close to the headquarters of the Skeptic Society, so we get a regular stream of atheists coming in. And we're also just next door to Fuller Seminary, so we get a lot of theology professors that will join us. It makes for a very entertaining time. And, Jorge, I'm going to ask you to put up my first slide. So, yes, that's great. You are going to have a time to field questions today, but if for some reason you don't get to have your question answered, I do take questions on both my Facebook and Twitter pages. And yes, Reasons to Believe does have a 24/7 YouTube channel, and if you subscribe, you'll be alerted to all the new videos that are coming out. So this talk is going to be just hitting a few of the points that's in my book, Weathering Climate Change. It's kind of a sequel to this book, Improbable Planet. There was one chapter there on climate, and now I've expanded that into an entire book. And if you go to reasons.org/Ross, you can get a free chapter of both Improbable Planet and Weathering Climate Change. And free chapters of several other books as well. And John, you're talking about the cold weather that you're having. This is a photo I took of my wife, Kathy, on August 1st. So it was 80 degrees the day before. And because we're in the mountains of British Columbia, you do get these weird events where the temperature can drop by about 80 degrees in just 1 hour. And so on August 1st, we had 8 inches of snowfall. It was below freezing. And the next day it was back up to 80 degrees. Climate is an incredible thing. So, and if we go to the next slide here, this basically is the title of my talk. How can we weather climate change? How can we sustain climate change? And a lot of people referred to my book as the anti-Al Gore book, where Al Gore put out his book, An Inconvenient Truth, basically making the point we're facing a crisis, and I do agree with him. There is a crisis before us, but he was recommending that all the nations of the world dramatically limit their living standards, basically drop the economic productivity of the world by a factor of 2 or 3, and that will stabilize the climate. And my problem with that as a believer is that he's overlooking the fact that we humans are fundamentally selfish, and trying to get billions of people to make draconian economic sacrifices is not something that's going to sell. And so basically I describe in my book, Weathering Climate Change, is ways we can stabilize the climate while we boost the world economy, while we give people a strong economic incentive to stabilize the climate. So if we go to the next slide, it basically shows you that we are in an ice age cycle. North America is the one continent that's most strongly impacted by the Ice Age cycle. This shows you where we are right now. 10% of North America is covered with thousands of feet of ice. But if you were to go back just 26,000 years ago, this is what North America looked like. Next slide. Where 55% of North America was covered by thousands of feet of ice. And actually, those thousands of feet of ice extended all the way down to Southern California. It was a retreat of that ice that carved out, for example, Yosemite Valley. And the port of San Diego was clogged with ice for 6 months of the year. Even down into Mexico, we have ice in the wintertime. And this is what it looks like right now. Next slide shows you that in the Ice Age, we oscillate between about 10% of our planet being covered with ice and 20 to 23% of our planet being covered with ice. And this slide shows you that it's about a 100,000 year periodicity. And you want to note here that for about 90% of that 100,000 year period, our planet is covered with 20% or more of ice. And for about 5 to 10,000 years, it's covered with 10% ice. And we call that an interglacial. The interglacial is where you have 10% ice. A glacial is where you got 20 to 23% ice. And what I write about in weathering climate change is if you want billions of human beings to be able to exist on our planet at one time, we must be living during an ice age cycle. It's a cycle of going from 23% ice to 10% ice and back down to 23% ice. This is what makes it possible for billions of us to live and live at a relatively high standard of living. I don't have time to give you all the benefits. There's over 15 specific benefits we can identify from being living in an ice age cycle, but I'll give you just a couple. The next slide shows you that it's the melting of glaciers left over from the last ice age that waters the great agricultural plains of the earth. We simply wouldn't be able to feed the population of the world and all of our animals if it wasn't for the fact that we had the benefit of ice left over from the last ice age melting and feeding the great rivers of the earth that water the agricultural plains. I mean, this is true of North America. We still have ice left over from the last ice age in the Rocky Mountains, for example, and the melting of that ice is feeding the great rivers that water our agricultural plains. Much more dramatic example would be India and China and Southeast Asia. 20 massive rivers flow out of the ice cap over the Himalayas and the Tibetan Plateau, and that feeds 20 major rivers of the earth. And without the flow of that meltwater, it simply wouldn't be possible to grow the food that feeds 3.5 billion people in Southeast Asia. And one of the things that's been recently discovered, this map here shows you the extent of thousands of feet of ice during the last ice age. And what we notice with the ice age cycle, and particularly the last ice age cycle, is that ice melts very rapidly. We're talking like 1,000 years. Thousands of feet of ice over Canada and Siberia and other places of the world melts quickly. And that rapid melt of ice causes a rebound in the elevation of the continents because the continental land masses here have been pushed down by the weight of thousands of feet of ice. And when that ice melts, you have a release of pressure and the continents bounce back up. And it's a relatively rapid bounce up, and that bounce up ignites volcanic eruptions all over the world. And so you get this volcanic dust falling over the great agricultural plains, and it's nutrient rich. I mean, that's one reason why people like to live near volcanoes, is because they know they're going to have really rich soil there. And also, that rapid melting of ice causes a strong wind to blow off of the high plateaus where the ice used to exist. This is particularly evident in Tibet. The release of that ice generates a huge wind that brings nutrient-rich dust and dumps it over the plains of China, India, and Southeast Asia. So these are just three of the benefits we can discern from living in an ice age cycle. Our great agricultural plains get regularly watered and they get regularly fertilized, and that makes it possible for us to feed the billions of human beings. Now, one benefit that's been overlooked a lot by the scientific community is that living during an ice age, and keep in mind that we are living in an interglacial that follows the most severe ice age in the entire ice age cycle. And we had the most rapid melt of ice from that ice age. And what that did is it carved out magnificent harbors all over the world. You may have heard of the fjords of Norway. Well, you also have fjords in Japan, also have them in British Columbia. I have them on, in Newfoundland. And so it's a carving out of these great harbors that makes it possible for the shipping industry to operate the way it does. And also it creates scenic wonders all over the world. So for example, in the next slide, this is Yosemite Valley, and it's relatively recent. This was carved out just thousands of years ago with a retreat of ice from the last ice age. And all over the west, we see these magnificent canyons carved by the retreat of ice. And this next slide that follows shows one in Canada that I visited a couple of years ago. And this is a canyon. It's quite remote, but you actually walk through this canyon. It's 3 miles long, and the walls jump up 2,000 vertical feet, and you can't see all the waterfalls there, but there's literally 25 major waterfalls that flow over the canyon walls from the glaciers above. And as you walk through this canyon, the canyon floor is loaded with wild strawberries, raspberries, and blueberries, gorgeous flowers. I mean, I can't tell you how restorative it is to one's soul to walk through that thing and see that. And it's like God knew ahead of time that there'd be billions of us living in dense metropolitan cities, facing stress from our work there, and that we would need relief. And thanks to the last ice age, we have these magnificent retreats we can go to. There are other examples besides canyons, but this just gives one example. Now, one of the problems of trying to be in an ice age cycle is that there's only a few times in the history of the Earth where we've been in an ice age cycle. In fact, the only time where it's been stable has been the last 2.5 million years. And the miracle of being in an ice age cycle has to do with the physics of the sun. And so if we go to the next slide, basically shows you the solar flare activity over the history of the Earth. And Jorge, I'm going to ask you to do one more click so that people can actually see. Thank you. And this is logarithmic. And so what we see in the activity level, the sun begins with a level of flaring activity that's 100,000 to 1,000,000 times greater than it is right now. And as you see, it dissipates fairly quickly, but still we're looking at tens of thousands of times greater than it is right now at the origin of life. But the origin of life is the origin of bacteria, and bacteria can handle a lot of radiation from the sun, because with solar flare activity you also get X-rays and ultraviolet radiation, but the microbes can handle that. That's one reason why we see on planet Earth nothing but microbes for the first 3 billion years of history of life on planet Earth. And I won't go into the details, they're covered in Improbable Planet, that 3 billion years of bacterial activity on the surface of the Earth is crucial for preparing for the introduction of plants, animals, and eventually human beings. But what this graph indicates is that right now, in the history of the Earth and the sun's flaring activity is at a minimal level. In the future, it's going to go back up, but right now it's at a minimal level. And this is true of stars in general, that when they're halfway through their nuclear burning is when their flaring activity is minimal, when their X-ray and ultraviolet radiation is minimal. And this is exactly what we need for human beings to exist, to be at this minimal level. And the next slide just shows you how fortuitous our present epoch is. The flaring minimum occurs when the sun is 4.57 billion years old, and recent observations of neutrinos and photons coming out of the sun establishes that the sun entered an extremely stable luminosity phase beginning about 50,000 years ago, and this is going to last for about another 50,000 years. So there's a really narrow window in the history of the sun where the sun's luminosity stability is sufficiently stable to enable the possibility of global high technology human civilization. We're in that tiny window right now. But the problem in terms of trying to get an ice age cycle is as the sun gets older and older, it gets brighter and brighter. And this is illustrated in the next slide, basically showing you how the brightness of the sun varies throughout its history. And what you notice is throughout the history of life on planet Earth, the sun has been getting progressively brighter and brighter. And for 90% of the history of life on planet Earth, our planet has had no ice at all. For only 10% of its history does it have ice. And so the enigma is, here we have the sun brighter than has ever been in the history of life, and yet we got ice on planet Earth. And so many of the chapters of the book focus on the miracle of how we have ice, and especially an ice age cycle at the moment in the history of the sun when it's brighter than it's ever been before. But keep in mind, if you want human life, you have to have it at this time, because that's when the flaring activity is sufficiently minimal to allow for existence. And so I won't go into all the details. They're described in Weather and Climate Change, but I'm going to focus on three major collision events between large asteroids and comets on planet Earth that make a major contribution to explaining how the surface of the Earth can be made cool enough in spite of the very bright sun at this time so we can have an ice age cycle. And I'm going to begin with the first. It was actually discovered by accident. There was a science exploration ship that was cruising in the southwest Pacific Ocean, and they discovered that there was an unusual anomaly 17,000 feet below the surface of the Pacific Ocean. And they went back there and discovered that there were isotope signatures there that a major asteroid had struck. And they were able to date that asteroid and discovered that the asteroid was quite large, a minimum of 1 kilometer in diameter and probably more like 4 kilometers in diameter, that if it hit on one of the continents, it would have created a crater at least 35 kilometers in diameter. And the bottom of the ocean floor, 17,000 feet below the surface of the ocean, they found 500 square kilometers of little pieces of rocks that had been remaining from this collision event. And a number of papers have been published just describing the impact that this collision would have had on our planet. Number one, it generated a massive tidal wave, 1,000 feet high, that radiated throughout the Pacific and the Atlantic Ocean, and actually struck even in the Mediterranean, in the Adriatic. They have found at the north end of the Adriatic that there is evidence that a 1,000-foot high tidal wave had deposited mud up that high. And it would go through these 17,000 feet of water, strike the bottom, stir at the bottom, and wound up throwing aerosols into the atmosphere. And these aerosols were so extensive and dense, it literally caused the equivalent of a nuclear winter. So much aerosol in the atmosphere that blocked out sufficient light from the sun that it basically made it winter all the time for several years. And this really is what caused Antarctica to be covered with much more ice. There was ice before in Antarctica, but it was this event that caused the extent of the cap of ice over Antarctica to get as big as it is today. And also this launched the development of ice over the Arctic Ocean and built up ice over Greenland. And this is the beginning of the Ice Age cycle. Before this hit, there was no Ice Age cycle, but it's thanks to this massive asteroid collision that it initiated this cycle of the planet going from a lot of ice to a little bit of ice and a lot of ice again, with a period of about 41,000 years. And it's this next event, another one, and this time we're looking at a comet. And one reason why we think it is a comet, next slide please, is we actually see two craters, and there may be more. The major crater we see is in the Spratly Islands. And if you're aware of the geography there in the South China Sea, there's these little tiny islands where you see that red dot there. But we now know that there was a much bigger island, and this massive comet that hit there basically obliterated this big island and left these tiny islands behind. And that red circle you see there is the minimum crater size. The blue is the maximum size. But if you look off to the left and up a little bit in Laos, you'll see another crater site. That little ellipse, blue ellipse there is a second crater site, which tells us this collider was most likely a comet, because when a large comet goes through Earth's atmosphere, it's quite typical that it will split into pieces, 2, 3, 4, 5 pieces. And there may be more pieces to this asteroid collision, but these are the two that we've found so far. But what it did is it caused a massive debris cloud to be sent up into the solar system, and our planet Earth goes through that debris cloud about once every 100,000 years. Now, that's not the only reason for the change in the periodicity of the Ice Age cycle. If we can go to the next slide, it shows you how, yes, 2.5 million years ago, the Ice Age cycle had a periodicity of 41,000 years, which means the warm interglacials only last 2,000 or 3,000 years. That would not be enough time to launch and sustain human civilization. But this giant comet that struck 800,000 years ago changed the cycle from 41,000 years to about 100,000 years. And now it's possible to have a warm interglacial long enough that humans can launch and sustain global civilization and build up a large population. And the book, Weathering Climate Change, actually described 14 different factors that played a role in changing the periodicity from 41,000 years to 100,000 years. But this collision in the South China Sea was probably the most significant of those effects that changed the periodicity. And the next slide shows you the actual temperature records throughout the last 3 Ice Age cycles. And what it reveals is that when you come out of an ice age, the temperature rapidly rises by 10 or 12 degrees centigrade, and it hits a peak that's about 2 to 3 degrees centigrade above the temperature we're experiencing right now. And when it hits that peak, the temperature rapidly drops, and you go back into an ice age that lasts about 90,000 years. And the slide that follows shows you what was going on during the last ice age. And here I've shown you the detailed temperature records from deep ice cores, and we see these all over the world. It's not just in Antarctica and Greenland now. We have records in the Himalayas as well as in the Alps and in North America, revealing that indeed worldwide we see dramatic temperature fluctuations. So what we're seeing here is the global mean temperature during the last ice age. And it basically shows you why humans during the last ice age were not able to launch global civilization. The global mean temperature was jumping up and down by about 10 degrees centigrade on time scales of 1, 2, or 3 centuries. That kind of climate instability meant that farmers could not depend on a crop they planted producing. And so we now know is that people during the last ice age indeed were planting crops, but planting many different species, and realizing that if they planted, say, a dozen different species, 9 of them might fail because of climate instability, 3 might actually produce, and they would try to feed their families on those 3. We now know that humans living during the last ice age, we got data going back at least 35,000 years, that they were involved in planting grains, harvesting grains, roasting those grains, grinding them, and turning them into bakery products. So this idea that only humans in the last few thousand years were technologically capable, we now know is a myth. During the last ice age, humans were technologically capable, but everything was done on a very small scale. Nothing could be scaled up because of extreme climate instability. And so if we were to go to the next slide, it shows you how this extreme climate instability transitioned. And so that pink ink you see over there on the left, that's typical of what happens throughout the entire ice age cycle, both the glacials and the interglacial, where the global mean temperature is rapidly jumping up and down by 10 or 12 degrees centigrade. But what you see here is that beginning about 9,500 years ago, everything changed, where instead of the global mean temperature jumping up and down by 10 or 12 degrees, it's been incredibly, extremely stable throughout the last 9,500 years. This is based on the latest temperature data. I planned to bring out this book actually 3 years ago, but I waited because I wanted to make sure we had really reliable temperature records. And so we brought the book out right after those reliable records became published. And we now know, for example, that the last 9,500 years, the global mean temperature has been stable to within plus or minus 0.65 degrees centigrade. The old texts on climate were saying plus or minus 2 degrees. We now know it was 4 times more stable than that, about plus or minus 0.65 degrees. And it's this extreme climate stability that made possible the global high technology civilization we have today and the high population. And we now know what was the cause of bringing about this extreme climate stability. If we can go back to that slide, you'll see that I got a couple of dotted lines there, and it basically shows you that the global mean temperature was rising rapidly, as is typical when you come out of an ice age. But instead of going up to a peak, 2 or 3 degrees centigrade above where we are now, the temperature suddenly plummeted, and it plummeted by about 10 degrees centigrade. So instead of being 2, 3 degrees above where we are now, it dropped down to 7 or 8 degrees below where we are right now. And that little dotted line feature there is referred to as the younger Driest cooling event. And geologists knew about this for the past 40 years, but they had no idea how to explain it. The explanation again came about by a serendipitous event. NASA was flying one of its aircraft over northwestern Greenland, and they happened to have their deep penetrating radar turned on, and they said, wow, we see something underneath the Greenland ice that we had never noticed before. And what they saw was a major crater underneath the Greenland ice, and the next slide actually shows you the location of where that crater is. Underneath 3,000 feet of ice, this ice penetrating radar had spotted a crater that is 32 kilometers in diameter. The next slide actually shows you a close-up of the crater location. And they sent a team of geophysicists after that NASA flight, and they went to the edge the western edge of that crater, and the meltwater coming out from underneath the ice had all the signatures of a huge stainless steel asteroid. And they estimated that the asteroid was about at least 1.5 kilometers in diameter. They were able to date when it hit, that it hit about 12,800 years ago. And this actually explains why we didn't go up to the normal temperature maximum of 2 to 3 degrees centigrade above where we are right now. The next slide shows you what was happening in North America at the close of the last ice age. Thousands of feet of ice were rapidly melting, and the melting of that ice caused a gigantic lake to form in central North America. It's got a name, Lake Agassiz, and this is a huge lake filled with cold glacial meltwater. And before this asteroid hit in northwestern Greenland, that glacial meltwater was going down the Mississippi and flowing out into the Gulf of Mexico. But this asteroid struck over thousands of feet of ice and caused a huge amount of ice to be deposited in the North Atlantic, which had an impact on cooling the North Atlantic, but it also caused huge chunks of ice and boulders to bombard all of the northern part of North America. And the result was that bombardment blocked the flow of meltwater down the Mississippi and into the Gulf of Mexico, and opened up two more channels of release of that cold glacial meltwater. One channel was released through the Great Lakes and the St. Lawrence River, the other through Great Slave Lake and Great Bear Lake, out through the Mackenzie River into the Beaufort Sea, just around the Yukon and Alaska area. And the result was it caused, at that time, there was a strong current in the Canadian Arctic archipelago that caused that cold meltwater that was being deposited in the Beaufort Sea to flow between Baffin Island and Greenland and out into the North Atlantic, where it joined the cold meltwater flowing out from the St. Lawrence River and bypassing Newfoundland. And the combination of the dumping of ice from the collision and then the flow of water coming out of the Beaufort Sea and the St. Lawrence into the North Atlantic, it turned back the Gulf Stream. And all of you probably remember your junior high education or earlier, where you were told one reason why Europe is as warm as it is and parts of North America are as warm as it is, you got this Gulf Stream bringing up nice, warm, tropical Atlantic Ocean water up into the north. But it was a combination of these three deposits of cold glacial meltwater in the North Atlantic that turned that back. And what it did is it brought about this 1,200-year period of cooling over North America, Europe, Siberia, and latest research papers tell us it was a worldwide event. So if I can go to the next slide, it shows you that this younger Driest cooling event that lasted 1,200 years was indeed global. We now know from our research on this collision, this Hiawatha glacier collision in northwest Greenland, indeed was responsible for this 1,200-year period. A couple of things this did. It prevented the global mean temperature from going up to its normal maximum. And the problem with that is, if you go up to that maximum, it melts the polar ice cap. And when you melt the polar ice cap, instead of the Arctic Ocean reflecting sunlight with 60% efficiency, which is what happens when it's ice covered, when the ice is no longer there, the liquid water reflects sunlight with only 6% efficiency. And what that does is it causes a huge increase in water vapor over the Arctic. And what that does is it dumps a lot more snow over North America and over Greenland. And by the way, I don't think you can blame what's happening to you there in Texas from what's happening in the Arctic. But what happens when you melt the polar ice cap? This actually causes a rapid drop into the ice age. But thanks to this Hiawatha collision event, that did not happen. Also, this Hiawatha collision event, when we came into the cooling event, the warming continued, but by now we're beginning to see a change in the normal cooling cycles. What generates the ice age cycle predominantly is the change in the tilt of Earth's rotation axis and the change in the shape of Earth's orbit. And so it goes up to a point where you reach a maximum, but now what's happening is the tilt of Earth's rotation axis and the changing shape of Earth's orbit is cooling the planet. And so instead of it going up to its maximum, it didn't, but it also generated a brief period where the climate suddenly stabilized. And when that happened, humans launched civilization. It's called the Neolithic Revolution, where people for the first time begin to specialize and say, we're only going to grow wheat. And we're not going to grow it over just 1 or 2 acres. We're going to grow it over hundreds of acres. And for the first time, farmers could produce a surplus of food and begin to use that surplus to trade. And so humans were beginning to say, hey, we can specialize. So you had humans that were just saying, all we're going to do is goats. We're going to raise goats, raise cows or horses. And then yet, first time you had cities that were developing where they said, we're not going to grow any food at all. We're going to produce tools and pottery. And people began to trade. This is the first time you actually see villages and cities and trading instruments, shipbuilding, because now we had the climate stability that would actually permit specialization and the scaling up from just say 1 or 2 acres of agriculture to thousands of acres. What this did is it not only launched civilization around the world, it generated through human activity warming effects that compensated for the natural cooling. So the reason why we've had these 9,500 years of extreme climate stability is that the normal cycles have been cooling the planet and normally would have cooled it by 10 or 12 degrees centigrade, but that was blunted by the fact that humans were now cutting down trees, converting it into grasslands where they could grow grains. They were domesticating cows and domesticating rice. And all these had the effect of warming the planet. When you domesticate rice, you release a lot of methane into the atmosphere. That's a powerful greenhouse gas. When you domesticate cows, cows emit huge amounts of methane and carbon dioxide, especially when you breed them to be milk productive and meat productive. So before cows were domesticated, you'd be getting maybe a gallon or a few quarts of milk a day from the cow. Human breeding brought that up to above 80 quarts, but bringing it up to 80 quarts meant that the cows were now emitting way more methane and carbon dioxide than they were before. And so I won't go into all the details, but as we see the growth of the human population and the acceleration of human technology, this all had an impact of increasingly warming the planet. Meanwhile, the natural cycles were working to increasingly cool the planet. But the miracle is these two perfectly counterbalance one another for the past 9,500 years. And if you look carefully at that blue line there, you actually see there's a slight decline. The temperature reached a maximum 8,700 years ago. And since that time, the climate, global mean climate, has been very, very slowly declining. In fact, it took 9,000 years for the temperature to drop 1 degree centigrade. If you look at the very end of the left-hand, right-hand side of that curve, you'll see in the last 70 years, it's jumped up by 1 degree centigrade. So it took 9,000 years to decline by 1 degree and just 70 years to go up by 1 degree. And the reason for that is human civilization for 9,000 years has been experiencing a gradual growth, But in the last 70 years, it's been an exponential growth. And it's that exponential growth, also the increase of our population, that reverse things. So right now, the global mean temperature is as warm as it was 8,700 years ago. And that's not a problem. The problem is if this last 70 years were to continue for another 70 or 100 years, now the global mean temperature would rise to a point where it would threaten the melting of the polar ice cap. And if that were to happen, we would see much more snow falling over North America and Siberia. The only reason we're not in an ice age right now is the amount of snow falling on Canada and Siberia only amounts to the equivalent of about 10 inches of precipitation per year. It's not enough to cause accumulating ice. But if that were to change to 20 or 30 inches equivalent precipitation, very quickly North America and Siberia would be covered by thousands of feet of ice. But this is the miracle of the, planet Earth has never had this before. This is the only time in the history of the Earth where we've been in an ice age cycle and we've had this extreme climate stability. So this is the anomaly, but it's an anomaly that's been brought about by literally a dozen simultaneous natural events that have not happened before. I mean, one of the things I talk about in the book is typically you get a big asteroid like that hitting the Earth about once every 25 million years. We had 3 hit within the last 2.5 million years, and they hit at just the right time and just the right location to bring on this period of extreme climate stability. And humans weren't aware that the planet was cooling thanks to natural cycles throughout almost the entirety of the past 9,500 years. And yet the development of human civilization just happened to perfectly compensate for the naturally cooling. Do you think someone was actually in control of all that? I do believe this is the hand of the Creator, making sure that the growth of human activity was perfectly counterbalancing what's been going on. And I have a chapter in Weathering Climate Change saying, we know this is the miraculous hand of God because this isn't the only miraculous thing going on in the past 10,000 years. The past 10,000 years has been remarkable for what's been happening on the sun, what's been happening on the Earth, what's been happening with these asteroid collisions, what's been happening with tectonic events on the continents of the Earth. And I'll just give one more. You'll find about 20 of them in the book. But it's also a period when we've had no nearby supernova eruptions. And so the next slide basically shows you what a supernova is like. And, Jorge, if I can get you to click one more slide, actually we'll give you a little bit of an animation here showing you a supernova eruption. A supernova is where a star will explode. A giant star will explode, and for a period of 9 months, it will shine just as brightly as 100 billion other stars in the galaxy in which it exists. And a paper published by an astronomer named Firestone basically made the point that relatively nearby supernova, next slide, are the norm. And so, for example, these are the supernova that have erupted in the last 45,000 years. And this is during the last ice age. And you can see that these supernova eruptions were occurring relatively close to the Earth, 360 to 820 light years away from us. Now, that's not close enough to bring about the extinction of human beings, but it is close enough to impact our health. It's going to raise the cancer rate, for example. But its biggest impact is the way it limits crop productivity. And so there's another reason why humanity was not able to produce the food to sustain a large population during the last ice age. There was all these supernova erupting, which would limit productivity. But Firestone was making the point, this is the way it is throughout the entire history of our galaxy during the history of life on planet Earth. This is the norm. In fact, he documented there was a minimum of 23 supernovae that exploded less than 1,000 light years from Earth during the past 300,000 years, and probably a lot more. The exception has been the past 10,000 years. So the next slide, for example, shows you the supernovas that have erupted. And what you see is, yes, supernovae are erupting in our galaxy, but none of them are close enough to pose a threat to human health or human civilization. The closest is a little bit more than 5,000 light years away. But this is the only 10,000-year window in the entire history of our galaxy where there's been no nearby supernova eruptions close to planet Earth. And why is this so? Why do we see all these windows opening up? Well, I'll just share with you one verse. Next slide, Revelation 7:9, where John has this vision. And he says, "Before me was a great multitude that no one could count, from a nation, tribe, people, language." And this is a reference to the number of humans that would receive salvation, redemption through the work of the creator of the universe. And the Greeks at that time had the capability of counting up into the billions. So it's basically saying it was God's plan all along that billions of humans would have the technology where those billions could hear the gospel message, respond to that gospel message, and become part of the redeemed host. Well, I'm going to end this talk in a couple of minutes, but let me just wrap it up by making some comments on how we can actually sustain climate stability without sacrificing the economy, in fact, boosting the economy. And the next slide shows you the Sahara Desert. And this is what, it's about the size of Australia now, actually bigger than Australia. And this is what it looks like. The map that follows shows you the extent of the Saharan Desert. And it's actually 10 times bigger today than it was 2,000 years ago. And the reason why it's gotten that large, people living on the south edge have been stripping the land of vegetation and using it for cooking fuel. And there was a point a few years ago where the Sahara Desert was growing by a rate of advancing south by 6 miles per year. It's not that great right now, but it's still getting larger and larger. And so what I mentioned in the book is that one of the ways that we could help replace and restore climate stability, go to the sub-Saharan peoples, give them all the kerosene they want to burn for free on the condition they work with us to replant the Sahara Desert. This is an example of how we could use fossil fuels and permit people to burn fossil fuels in a way to restore climate stability. Because within 20 or 30 years, we could actually shrink the Sahara Desert back down to where it was 2,000 years ago. And that means that we could actually plant grains over the Sahara Desert. During the Roman Empire time, what is now the Sahara basically fed Europe with the grain that it produced. This would provide an income for the North African peoples, and it would soak up huge quantities of greenhouse gases with all that plant matter over a desert that has virtually no plant matter right now. So this is an example of a win-win solution. And likewise, the next slide shows you the jungles of the Amazon, and the following slide shows you that the Amazon jungles cover 5.5 million square kilometers. It adds up to over half of Earth's rainforest. However, people have been cutting down the forest. Next slide. And so we show that there's been a 20% loss in the Brazilian Amazon forest in just the past 50 years. And if this were to continue, the Amazon forest would actually be turned into a desert. And by the way, this is also happening in North America. Next slide shows you the rainforest, the temperate rainforest of North America. And what you notice, and this is true of the Amazon as well, in the regions where they're, quote, protected, you get this accumulation of dead large trees, and it decays and releases greenhouse gases to the atmosphere. So one way we could better manage the Amazon, instead of cutting down the trees and turning it into pasture land, where the pasture land will be productive for only about 10 or 20 years, and then you got a desert. Instead, we go into these rainforests, and what you do is you selectively cut down the largest trees in the forest. Not all of them, because you need to leave a few of them for habitat space, but you cut down select ones. These are the ones you're going to make the most money out of because they're big trees. But what we now know is that the largest trees in a rainforest are ones that are growing the slowest, and therefore they're pulling the least amount of greenhouse gases in the atmosphere. If we were to harvest them, they could now store carbon as furniture and homes and building materials instead of dying on the floor of the forest and releasing greenhouse gas in the atmosphere. You replace these cut down big trees with seedlings and young trees, and these trees actually pull 2 to 4 times as much greenhouse gases out of the atmosphere. So there's a healthy way to manage these rainforests so that they produce the maximum income for the people that lumber the area, but also pull the maximum amount of greenhouse gases out of the atmosphere. And so we can go to the next slide, and the next slide, and this is what I'm going to close with, is that we have this idea. In fact, the new administration that comes in is saying we're going to go wind and solar over the whole country. And I critique the problems with wind and solar energy generation in the book Weathering Climate Change. The problem with wind is those windmills kill a lot of birds, and it takes a lot of carbon consumption to sustain those wind vanes. They have to be replaced. And so the carbon footprint for wind generation is not trivial at all. If you've ever been to a wind farm, what you notice is typically 3/4 of the windmills are not turning. Why? Because they have to be tuned to a particular wind velocity. And nowhere in the world do we have just a single wind velocity. It always changes with respect to time. The problem with solar, too, is that it takes a lot of carbon to build these solar panels. And if you put them over the deserts of the world, it impacts the ecology there. You put them in other places, it impacts the ecology. On the other hand, I'm all for putting solar panels on roofs of buildings and of factories because you actually can't have an ecosystem under that anyway. And now there's a new technology where you don't put panels on your roof, you basically replace your roof. And 100% of your roof generates electricity instead of just, say, 50% of your roof. But I think the real breakthrough that's going to help us eliminate our need for fossil fuel burning to sustain our energy is thorium nuclear power. I only hint at this in the book. Next slide. A lot had to be cut from the book. I wish I'd kept this in the book because there's been research done just in the past few months showing that this really could be the answer. Thorium is much more abundant on the Earth than uranium is. 1 ton of thorium generates the energy equivalent of 200 tons of uranium or 3.5 million tons of coal or of oil. The advantage of thorium nuclear power generation, it's impossible to have a meltdown. It's impossible to develop weapons from thorium nuclear power generation. You're not going to be able to make a weapon. It's safe to mine the thorium. You don't have to wear special equipment. The employees in the reactor don't have to wear special equipment. And the radioactive waste is a whole lot less of a problem than the case with uranium. It's actually safe to touch after 200 years, and in some cases only 50 years. Compared with uranium, where you have to store the radioactive waste for at least 50,000 years. In the case of thorium, you have a much more limited storage time. And with that, I think just go through the rest of the slides here, and we'll close. Just remind you again, next slide, that you can get a free chapter of these two books just by going to reasons.org/Ross. So with that, I'm going to turn it back to John and our Q&A time.
That was excellent. Thank you very much. I enjoyed that. It was fascinating. The last part on thorium, especially, as you mentioned, that was not in the book, and I think that's the first that I've heard that. So I'll look hearing more about that, hopefully in the coming months or years. So during the Q&A, everybody in the Austin chapter knows that as the chapter president, I normally get to ask the first question, but this month I'm going to defer that because originally when we scheduled you, Peggy Lemons wanted to have you in. She and Bob Lemons are some volunteers for our chapter, and they're going to go down in the Hall of Fame of volunteers. And she wanted this to be a surprise for Bob to celebrate their anniversary. So I told them that I would defer and let them ask the first question. So let me for you now. So you mentioned we've basically had a stable climate for the past 9,500 to 10,000 years, which is a relative rounding error when you consider the time of the life of the planet. Yet we have this concern regarding global warming, and we want to change, quote, now. Now, in your book, you mentioned numerous ways to reduce greenhouse gases, and many of these examples could take hundreds of years to make an impact. Now, we're a civilized world, and we've come to expect instant gratification, and we're also a what's in it for me society. So to make some of the changes are political hot buttons and require economic investment. So this is a two-part question. I'll read the first part and let you answer that, and then the second part. So the first one, could you elaborate on some specific economic challenges and economic benefits of one of your proposals of prolonging climate stability? So maybe going a little bit more depth on one of those proposals at the end.
Well, I ended it with this reference to thorium. If we were to scale up thorium nuclear power gen, by the way, we had thorium nuclear reactors in the US in the 1960s. So it's not a new technology. The reason why it was never developed, you can't make weapons with thorium. So they said, yeah, we're going to go with uranium because we can get weapons. With thorium, you can't. But now that's an advantage. That means we could send thorium nuclear reactors to third world countries without running the risk that they're going to use them to develop weapons. And where do you get the economic incentive? Thorium nuclear power generation has the potential to generate electricity for less than half the price of water power. Water power today delivers the cheapest electricity on the planet. So cheap, for example, that in parts of Canada, where all their electricity comes from water power, you can drive a 5-passenger Tesla for 300 miles for a cost of less than 50 cents. So if we could actually come up with power generation that's orders of magnitude cheaper than the money we're paying for power right now, people are going to say, hey, let's do this. And that's kind of the point of my book, is that we need solutions that can be implemented fairly quickly. If we wait 50 years, that's too long. And the only way you're going to get immediate action is to give people a strong economic incentive. And with a strong economic incentive, there's no need for a government to get involved. It's like, okay, if you come up with a solution that stabilizes the climate, that benefits the ecosystem, and makes a huge boost to the world economy, what politician in his right mind is going to vote against it? I mean, whether you're a conservative or a moderate, you're going to say, hey, go for it. And so I mean the politics out of it. And that's kind of my point in the book, is that if we're going to actually resolve this problem quickly enough, we have to do it in a way that we take the policy problem. Yes, politicians have to be involved if you want to enforce draconian economic sacrifices. But politicians don't have to be involved if people say, you know what, I can invest $1,000 in this, and I know within 3 years I'll get 3,000 back. It's like, they're going to go for it. I mean, what we know from economics, if you can get a 7% return in a year, that's enough to motivate people to go for it. And the solutions I provide in the book are way better than 7% per year on your investment.
So as a follow-up to that particular answer and question, so again, I had never heard of thorium before today and this possibility. So what's preventing us from moving forward on that? Why aren't we hearing more about that solution?
Well, you're beginning to hear about it now because, number one, the countries of the world that have a lot of thorium, the U.S. has a lot, India has a lot, so India's saying, hey, let's look into this. Israel is looking into it, Canada is looking into it. So there's 5 nations of the world are actually giving this some serious attention. And you say, well, what's the possible holdup? Well, we don't have complete knowledge of how we can scale this up and what the impact would be of scaling up, because we've had small thorium reactors in the past, but can we scale them up by a factor of 100 times to generate really significant sources of energy? But engineers I've talked to have said we don't see any potential problem. I mean, what I find enigmatic is for 70 years there's been a huge focus on trying to develop nuclear fusion reactors, but that requires making a stable magnetic bottle to house the nuclear fusion. And we're now realizing we may never come up with that. Billions of dollars have been spent, and hey, we'd be far better off pursuing thorium nuclear reaction because there is no major technological difficulty. There's simply the engineering problems of scaling up. I think that could be overcome literally within 12 months and that we could move forward. And there's enough thorium in the United States alone that it could produce 100% of our energy needs for a minimum of 1,000 years at a price that would be at least half the price of the cheapest source of energy we have today. I think once people realize this, they're going to say, let's go for it. And I mean, it's really the only way I see of limiting our need for fossil fuel energy generation in a short period of time. I mean, right now, 90% of our energy comes from fossil fuel burning. And if we're going to reduce that, I think this is the only way it can be done in a short enough period of time.
Interesting. So go to part 2 of their question. Part 2, so as a Christian, can you offer some suggestions on how we can engage people in a non-confrontational way to consider some of your proposals without getting into a political debate?
Well, I think the way to avoid the political debate is say, hey, would you like to hear about some win-win solutions? Everybody likes win-win solutions. I call this a win-win-win because it's a win for the climate, it's a win for all non-human life, the ecosystem, and it's a win for us. And it's a biblical principle. We were commanded by God back in Genesis, and the command was repeated in Job. We humans are on this planet with the mandate to manage the planet's resources for our benefit and the benefit of all their life. And how do you get the politics out? The politicians are saying we have to choose between our benefit and the benefit of all their life. Well, what if we didn't have to make that choice? What if we got solutions that are for our benefit as well as the benefit of all their life, as well as stabilizing the climate? With everybody wins, there's no need to get into a political fight.
Excellent. Thank you. So I tried to look for some critiques of your book and actually found a dearth. There were not very many critiques that I could find anyway. There was one-star review on Amazon. And so reading that, most of the teleological assertions in the book. However, he did have one comment that I thought you're obviously well qualified to speak in regard. So he notes that on page 223, Dr. Ross says this, quote, astronomical measurements firmly establish that fixed physical laws govern the universe. And then he makes this comment, astronomers are still arguing about whether the physical laws are, quote, fixed. This is not a settled matter in cosmology. For example, the Cambridge cosmologist Martin Rees, president of the Royal Society, says the laws of physics aren't absolute and universal, but more like local bylaws. varying from place to place on a mega cosmic scale. A God's eye view would show our universe as merely a single representative amid a vast assemblages of universes, each with its own bylaws. Now, I think that he's equivocating here, but I'll be curious to hear your answer.
Well, yeah, interesting comment, a rather surprising comment, because we have measurements that tell us that the laws of physics indeed have been fixed for the past 12.5 billion years, and fixed to within 16 places of the decimal. So they're not only constant, they're extremely constant. Now, what he's referring to is speculations. Okay, we can measure the constancy of the laws of physics in the laboratory, as well as out to distances of 12.5 billion years, in some cases out to 13.5 billion years. But there's certain physicists, he mentioned Penrose, there's others as well, that are saying, well, if we go back sufficiently early in the history of the universe, we run into what's called the quantum gravity era, where the dynamics of the universe is not dominated by gravity, but is dominated by a combination of quantum mechanics and gravity. And they're saying we don't have the instruments to make measurements of the laws of physics in that era. And so it's possible. Again, this is pure speculation. Maybe in the quantum gravity era, the constants of physics are different than what we measure now. Now, to show you the point of the speculation, the quantum gravity era refers to the first 10,000ths of a trillionth of a trillionth of a trillionth of a second after the cosmic creation event. So we're talking about the extremely early split second after the cosmic creation event. Once we get past that event, we know gravity dominates the dynamics of the universe, and our measurements tell us the laws of physics are constant throughout that era. But yeah, we don't have the measurements of the observations to see if the constancy of physics holds all the way back to t equals 0, the very beginning of the universe. So there's this tiny split second where things could be different. But 100% of our observations and experiments tell us no change in the laws of physics. And for those of us that are believers, that's a biblical statement. There are many places in the Bible, for example, Jeremiah 33 and Romans 8, that tell us that God has established the laws of physics. The laws that govern the heavens and the earth are fixed. As God says, I'm a God that doesn't change. If you want evidence, look at the laws that govern the heavens and the earth. As they don't change, I don't change. So this is a biblical principle. And I find remarkable as an astronomer, we can establish that principle throughout the spatial extent of the observable universe, all the way back as far as we can see. But we do not have the capability of seeing back exactly to the cosmic creation event. Our measurements peter out at about 100 billionth of a trillionth of a trillionth of a second after the cosmic creation event. But you know what that tells me, John? For 99.999999999, go on a few more 9% of the history of the universe, everything measures to be constant. And what I've written about in the Crater in the Cosmos 4th edition is that we actually are on the verge of penetrating the quantum gravity era with observations. And the two sources would be, we now have the capability to observe what's going on just outside the event horizon of supermassive black holes. And that actually gives us information of what happens in the quantum gravity era. Another place is when we look at the images of distant quasars. As light comes from a distant quasar towards us, it actually gives us information on the quantum gravity era. And for example, those that have speculated that the laws of physics are radically different in the quantum gravity era, what that prediction tells us is that the images of distant quasars will actually blur and not be sharp. That as they travel through intergalactic space, they will blur in proportion to their distance and also inversely proportion to their wavelength. Well, so far, all of our observations tell us those quasar images are sharp. We see no blurring, which is evidence that these speculations probably are not true. Now, are we ever going to be able to eliminate all the speculations? The answer is no. There's always going to be ignorance about the universe that atheists can appeal to say, hey, the Christian worldview doesn't hold up. But it's not based on empirical evidence. Basically, they're appealing to things we can't test, we can't measure, we can't do experiments on. And I think philosophically, this is where I come from, we have to base our beliefs on what we can see, test, and measure. And what's remarkable about the 21st century, we can observe and test and measure 99.99 and give you another 39% of the universe, and it shows us that everything the Bible declares indeed is consistent with these measurements.
So in setting up this next question, I'm curious, are you a sci-fi fan at all?
Well, my sons always say, Dad, we don't want to watch sci-fi with you because you keep telling us how many times per minute they're violating the laws of physics. But hey, if they're not violating the laws of physics too frequently, I can kind of go along with it.
I can see you being a killjoy watching that. That's good.
Sure.
One very popular sci-fi scenario is one where we have rendered Earth uninhabitable due to our mismanagement or a nuclear war or something. So we then move on to colonize other planets, such as Mars. Some celebrity scientists have speculated that this could be a viable option for the future of humanity. And given the large number of factors required to be just right to make Earth habitable, and even the greater number of factors required for advanced civilization, do you see any chance that we could develop the knowledge and technology required to terraform another planet like Mars?
Well, I've written in the past that it'd be far cheaper to build an artificial planet than to try to terraform Mars or some other place that we could go to. And one of the problems, I've written about this, there's an article on our reasons.org website. It's titled Gut-Wrenching Space Travel. And makes the point that once you get beyond the magnetosphere of the Earth, you get exposed to really deadly radiation. And it's one thing to go to the moon. When you go to the moon, you're outside of Earth's magnetosphere for just a few days. But if you're outside for 3 months or more, it's going to do major damage to your intestinal tract. They've done experiments on mice and rats, which are excellent proxies for the human digestive tract. You notice they eat virtually the same food that we eat. And what they discovered is after 3 months, the digestive tracts of these rats and mice simply don't function anymore. And the mice and rats are in excruciating pain, unable to function. And if you wait another 3 months, those rats develop malignant tumors in their digestive tract and they die. This is what's going to happen to a human once they leave Earth's magnetosphere. And we know it's going to take a minimum of 6 months to transport humans to Mars, which means by the time you get there, they're likely to be dead. And within 3 months, they'll not be able to function. So they won't be able to even manage their spacecraft. And people have said, well, why don't we build a spaceship with an artificial magnetosphere? Well, it's kind of the problem I mentioned about nuclear fusion. Nuclear fusion is all about building a small magnetic bottle. And what we're now discovering is, well, in order to have a stable magnetic bottle or a stable magnetosphere, you need a lot of gravity to stabilize it. The sun's got a stable magnetosphere. Earth has a stable magnetosphere. What stabilizes it is the huge mass of the Earth and the enormous mass of the sun. If you've got a spaceship, you simply don't have the mass to stabilize the magnetosphere. And so on that basis, I don't think we're ever going to be able to send people to Venus or Mars. The moon, no problem, as long as you don't keep them there very long. Bring them back quickly, we'll be fine. But Mars, I don't think we're ever going to do that. And in terms of the science, I see no need. We can learn everything we want to learn about Mars by sending machines and not sending people. So I think we're really stuck with this planet. We better take good care of it because there's really nowhere else to go.
Excellent. So, question from one of the audience members, and I believe that you actually addressed this in your book, but I'll let you answer this here. Have you seen the various geoengineering products that place various reflective metals into the atmosphere as aerosols? What is the viability of this method of reflecting radiation, and what are the long-term dangers?
Well, it is viable. In my book, I describe 5 different projects that are being proposed to basically shield our planet from solar radiation so that we can continue to burn our fossil fuels, warm up the planet, but compensate that by allowing less solar radiation get through to the surface of the Earth. In my opinion, the only safe option is one where we can control the amount of light coming through the shield that we put up there. And, the one proposal that does that is prohibitively expensive. It's basically putting shields with spacecraft far out between us and the sun, where they can control the amount of radiation that comes through the shields and then down to the Earth. One way that makes it a little more economic is to actually use that shield to generate electricity and then send the electricity down to Earth through microwaves. It's not that efficient, but it's probably the best option out there. And you've probably seen some of these sci-fi movies where humans actually did put up some kind of shield or aerosols in the atmosphere, and they wound up generating a way colder climate. And try to remember, there's a Korean filmmaker that made a movie about a train that was running back and forth where they did this very thing. They said, oh, the climate's warming, we need to cool it down. They put this thing up there, but they wound up making the planet much colder than what they intended. And then they wound up having this very severe ice age. And actually, I think the movie talks about how human civilization, humanity was threatened with extinction. So yeah, unintended consequences. I have a whole chapter in the book on unintended consequences, basically making the point, be very careful when you do these huge geoengineering projects that you might wind up getting something that you never intended to happen.
Another question from our audience. This is from Craig Andrews. Says, I'm intrigued by the flatness of the temperature over the last 9,000 years. It strikes my intuition that we've experienced multiple orders of magnitude increases in industrialization over the last 9,000 years, but we still see flatness in the temperature curve. How do you reconcile this?
Well, I think people aren't aware of just how dramatic are the natural cooling cycles. And so, for example, as Earth's rotation axis tilts from 24.5 degrees down to 22.1 right now, we're at 23.5, but we're heading towards 22.1. That is an impact of dramatically cooling the global climate. And so what's prevented that is that human activity has been dramatically warming the climate, and the two have canceled one another off. That's what explains that extreme climate stability over the past 9,000 years. The problem of the past 70, since World War II, there's been a tremendous acceleration in the development of human technology, and consequently the release of energy and the release of greenhouse gases into the atmosphere as a result of that huge burst in technology. I mean, I was born shortly after World War II, and just in my lifetime, it's just been incredible, the advance in technology. We've gone from horses 70 years ago delivering milk in bottles at our doors to where today we're sending spaceships to all the different bodies of the solar system, where our standard of living is literally 100 times greater than it was 70 years ago. I mean, just look at how people lived 70 years ago as to how they live today. You don't just have one car for every 10 people. People have 2 or 3 cars in their driveway. And, look at the development of technology. I mean, computers. The fact that every 18 months our computer capability doubles. I mean, that was unheard of 100 years ago.
I think I heard a statement once that people living during the Civil War had much more in common with people living thousands of years before them than they do with people today, because our industrialization has advanced so much and so quickly. That might explain why the last 70 years that arc has gone up as far as the temperature, is that we're finally overcoming that, right?
Well, I've got a thing in the book about Bitcoins. I mean, people don't realize how this Bitcoin currency causes a tremendous energy demand. And if we were to eliminate Bitcoin currency, that would have a major impact on dropping the release of greenhouse gases into the atmosphere. And that's a relatively new phenomena. How many people are aware of the huge energy drain of Bitcoin currency?
Yeah, I thought that was very fascinating in the book. So another question from a viewer asking about solar output. Aren't we at a solar minimum right now? Also, I wonder if anyone is measuring the magnetic flux of the planet that diverts many of the subatomic particles radiated by the sun.
Well, I do talk about the sun in the book. I mean, it has an 11-year cycle, and that does impact our climate, which is one reason why in the book I did 10-year rolling averages. That was designed to take out the variability in the global mean temperature as generated by the 11-year sunspot cycle. And one thing that concerns me is that I'm hearing that our nation is really trying to shut down fossil fuel production and go whole hog with solar and wind power generation. And this also, I think, has an impact with the proposal I make of thorium nuclear power energy generation, is that it means that we're going to be evolving our society to a total dependence upon the electric power grid. And the electric power grid is at extreme risk from a solar flare. Now, I mentioned we're at a solar flare minimum. Never in the history of the sun have we had so few solar flares, and flares that are relatively feeble in comparison to what's happened in the past. However, it's not a zero risk. Back in 1989, there was a solar flare that knocked out the Quebec power grid. The rest of the power grids were fine because none of them were close to the North Magnetic Pole. However, if we were to get a solar flare like what happened in 1859, that would knock out all the power grids of the world. Matter of fact, it would knock out those power grids to such an extent, it would take a total of 2 years to restore them. And that 2-year period, we would have huge consequences. Because for now, just look at the United States. There's no way we can feed 330 million people without reliable electric power generation. So I'm all for moving our energy dependence upon cheap electricity. However, we need to take steps to protect our power grids. The only power grid in the world that's adequately protected is the Quebec power grid. We should be protecting the rest of the power grids, especially if we're going to ramp up and have much more of an energy dependence coming from electricity. I mean, what happens, for example, if all the cars are electric and the power grid no longer operates? Then that means we have no transportation. The trains stop running, all the cars stop running, the trucks stop running. We would be in a huge amount of trouble.
Mm. Well, Jorge tells me that my video is having some difficulty, so we do apologize for that, but we'll continue. So this is an interesting question. After reading your book, I decided to look into ostrich meat to try out on my steak-loving husband. I was shocked at the prices. A pound of ground ostrich meat cost 3 to 4 times as much or more as a ground of lean ground beef, and there's none locally available, so I'd have to pay shipping costs in addition. So I understand that this is in part because the meat and dairy industries are subsidized, and I assume that the ostrich industry is not. But given that ostrich meat is not available to the average consumer, I wondered why you suggested it instead of plant-based meats, such as Beyond and Impossible, which are much cheaper than ostrich and are more readily available.
Yeah, again, it's a scale factor. The reason why ostrich meat is so expensive is that there's not much ostrich meat production going on, especially here in the U.S. But I make the point, if we were to scale it up to the size of, say, our beef industry, that ostrich meat would probably come in at about half the price of turkey. And turkey right now is a cheap meat market. So scale up ostrich meat production where it could be sold for half the price of turkey, then everybody'd be buying it. And it's the healthiest meat you can eat. And it's red meat. I've tasted it. It really is good. It has very little cholesterol, very low saturated fat, just as high in iron as beef is. Tastes like beef, tastes better than beef, in my opinion. So yeah, here's another thing that we could do. I think what's holding it up here in North America, incidentally, ostrich meat production is being scaled up in South Africa. But the people in South Africa are well aware you cannot treat ostriches like you do beef cattle. I mean, the thing with beef cattle is you can set them loose in a huge field and they're fine. But ostriches are highly social animals. They need to live close together with members of their species. They also need human contact. And so if you want to have a good ostrich farm, you need to make sure there's healthy social interaction amongst the ostriches. Typically, a male and a female ostrich will mate for life. So again, that's where it's different from cows. So as long as the farmer understands the biology of the ostrich, then they can actually make money on an ostrich farm. But there's many stories of failed ostrich farms in North America. But the reason for the failure, they're treating the ostriches like they are cows. If you do that, the ostriches get sick and you're not going to make money. And so just realizing that they're social animals and they need both contact with members of their species. If you make pets out of them, you're going to do great. If you ignore them and treat them like cows, you're going to go bang. But the Africans have kind of got this figured out, and we need to get that knowledge. By the way, one of the supporters of Reasons to Believe is a woman in Florida who's breeding ostrich pairs. But she says her frustration is when she sells the pair, the people really don't know how to take care of the ostriches. And so it frustrates her that so many of these ostrich farms in the U.S. are failing when there's no need for them to be failing. But that's the reason why they cost too much right now.
Okay. Another short question. So they've discovered a fungus in Chernobyl that eats the radiation. Does this shorten the time to which it will be safe to re-enter Chernobyl?
It could. I mean, there's bacteria that will eat uranium, for example, and they found these fungi that will do it. That will certainly help process the waste. I still argue that thorium is the option. Yes, there's these bacteria and fungi, but you're still looking at tens of thousands of years of storage problems for the radioactive waste. And they're much more dangerous than the radioactive waste with thorium. As I mentioned with thorium, you're looking at 50 to 200 years. And even if you're in come into contact with them, it's not going to be the same problem as coming into contact with the uranium waste. And the fact that thorium is far more abundant. And, I think this is actually a gift from God. Our planet Earth has 630 times as much thorium as what we'd expect in any other rocky body in the universe. We are living on the thorium champion of the universe. I wonder if that was God's intent all along, that He would provide us with exactly the energy source we need to solve the problem we're facing right now.
That is interesting. Another short question. This is a follow-up question to one of the responses before. So how do we measure the constants of the universe millions of years ago?
Well, we predominantly measure them through spectral line observations. So to give you an example of the velocity of light, you've probably heard of the Zeeman effect. where a single spectral line will get to be split into two spectral lines. The degree by which they are split depends on the velocity of light. And so if we can measure hyperfine split lines at great distances, that gives us a measure of the velocity of light deep in the past. And I think what's particularly fortuitous, one of the strongest lines we see in astronomy is the hydrogen line, neutral hydrogen line at radio wavelengths. That's one of these hyperfine split lines. And because it's neutral hydrogen, we can see it as far away as 13.5 billion light years. And we make those measurements, it tells us there's been no change in the velocity of light over the past 13.5 billion years. But likewise, we can look at other spectral lines to measure the fine structure constant, to measure the gravitational force constant, and we can actually measure them to extremely high precision.
Very good. So we will close out with this last question. This is coming from a bit of a skeptic or a skeptical point of view. So I think it's a good one to end with. So the petitioner says, I am old enough to remember the days when popular scientists told us that the Earth was cooling too rapidly to support human life and that we were overpopulating the globe. We now know that in many countries, the population rate is below the replacement rate, creating problems for their economies as their populations age. Further, the planet is dramatically warming, not cooling overall. This has left me skeptical that scientists have the ability to figure out what the future holds for a subject as vast and complicated as climate change. I feel manipulated by scare tactics, seeking to get me to endorse policy changes that, in caps, may save humanity in some distant future, while those policy changes can demonstrably harm some of the most vulnerable among us right now. Why should I believe that the scientists now have figured out the true factors involved in climate change and that we mere humans have the power to make changes that will alter something as large and complicated as the entire planet?
Well, I think he's making really good points. There's a need for caution. There's a need for research. That's why I devoted some attention in the book to unintended consequences. Is that, before you jump off on some major alteration in the world economy, let's make sure that we don't wind up with, really disastrous unintended consequences. His comment about the temperature, I made a comment earlier that I waited to bring out the book until we had reliable temperature records. And what has happened in the last couple of years is that climatologists have found not just one temperature proxy, but 74 temperature proxies. And instead of trying to determine the global mean temperature over the past 10,000 years based on just, say, ice cores in Antarctica, they're now looking at ice cores all over the world. And not just looking at ice cores, but looking at tree rings. Looking at varves. So they're actually looking at multiple different temperature proxies. And I think for the first time, we have reliable, indisputable temperature records for the past 10,000 years. And I've actually tested this on climate change deniers and just say, hey, look at the data and tell me what you think. And they come back and say, hey, this stuff is reliable. So it's actually helping to blunt the deniers that have been part of this. Where I see a shift in the denials is that we still have people out there saying, yes, the climate is warming, but we humans are not responsible. They're looking at non-human factors. And again, I spend some time in the book and saying there are non-human factors, but it's the human factor that is dominant. And it's the fact that the human factor is dominant actually explains why the climate has been so stable over the past 10,000 years. So again, certainly just alerting these deniers to the fact that the natural cycles are cooling the planet. The planet is obviously warming, and if the natural cycles are cooling the planet, there's got to be some other non-natural factor that's warming it, and that's us. But I think they are persuaded when they say, hey, this really explains this incredible balance over the past 10,000 years. And there's another part of that question I forgot, so if you could review it for me.
I think you addressed that. I think the biggest thing was, how much can we really control this? There's so many factors that are out of our control. How can we mere humans, actually control it um, moving forward?
Well, he did raise the point about the population. And, I'm friends with a person that spends his time researching population statistics. And his point is the birth rate, no matter where you go in the world, drops in proportion to the per capita wealth and the per capita technology. Wealth and technology drops the birth rate. The other thing that drops the birth rate is urbanization. When people leave the rural areas and move into the cities, they drop the birth rate. And his comment is it's all economic. If you're a farmer, you're going to want to have as many children as possible because it's going to help boost your income. But if you're living in a city, you don't want a whole lot of children because they're going to cost you a lot of money to educate and get them set up on their urban high-tech careers. And therefore, what you notice is in highly urbanized, wealthy, high technology areas, the birth rate is catastrophically dropping. Probably the best examples of that are Hong Kong and Singapore, where the birth rate is already down to just one child per woman, which means we're way below the replacement rate. And in every high-tech, wealthy nation of the world today, the birth rate is below the replacement rate, which means, in fact, my friend is saying, if this becomes a worldwide phenomenon, his point is even the poorest nations of the world are getting wealthier with more technology. And therefore, he says, by the year 2100, we could see the human population approaching just 1 billion individuals. We could really see a rapid reversal in the human population. And that's important to take into account in terms of what's going to happen to the future climate, because the population level is a major factor determining what happens to the climate. So we need to take that into account. And maybe we need to be looking at technology and wealth and urbanization in a way where it doesn't have such a strong factor in dropping the birth rate. That's a whole nother book that someone could write, how we could deal with that. But in terms of how we can move forward, my main point in the book is if we take those steps that we know will benefit the ecosystem, that we know will stabilize the climate, and that we know will boost the world economy, chances are we're not going to be facing these draconian consequences, unintended consequences. And if we take steps in that, and by the way, we begin to take those steps. So for example, I say with thorium nuclear power generation, let's get it going and test the benefits. What does it do to the price of electricity? How about the scalability? And is it really as safe as what we think it is? If we begin to increment, same thing with shrinking the Sahara and Gobi deserts. Let's get started and see what happens. And if it's going in the right direction, we can accelerate it.
Very good. Dr. Ross, again, thank you so much for sharing your wisdom and your time with the Austin chapter this morning. We'll have to try to get you back on the schedule to come back live and in purchase sometime in the future.
Well, I've had my first vaccine shot, so maybe that's actually feasible. We'll see.
Well, that is awesome to hear. Congratulations.
Thank you.
All right, Jorge, thank you very much.